Oh, I didn't add myself. Wonderful. Helmano. Nom, 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 nom. Uh, Elmano. Who are you? You want to join? I don't remember who you are. Mm-hmm, 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 mm-hmm. Let's ask Judas if he wants to join. Andrew. Okay. I was just listening to who is she? Here, I'll show you. Really interesting. I love these discussions about pseudo intellectuals. I just love. Uh, what we have 3 people watching already. Well, that's exciting. Does anybody want to join? Do you want to join me? Join me. Join me. Uh, Let me see. Pay me. Anyway, what was I watching? Let me show you. Can I see what I was watching from here? No, I want to see the history. Hysterectomy. Her. I was watching her. I was listening to Dr. Avi. Ukraine. This is no, not this. Must have been watching this. When did I watch this? I don't remember watching this. This is interesting. When is this is when age becomes a barrier to learning. Very good, very good. Definitely recommended. He doesn't even say learning math. He says in general, when is age a barrier? Destiny. Oh my god, this is so wrong. Destiny is so wrong about Tim Pool. He's getting the whole thing wrong. Destiny. Oh, you are my destiny. Okay, let's see what I got. Wait, what percentile? 65? Okay. So let's watch on the phone. I'm gonna set my own video. One, two. So let's watch on the phone. Okay. So we'll watch it on the phone. So if somebody says something, we'll get a notification. I don't know. I don't know how to do this. I don't know how to get a notification. This is like the dumbest thing on YouTube is that there's no. It doesn't play a sound, and StreamYard does the same. I mean, there's no indication. You would think StreamYard, you pay them for a service. You would think they would play a sound when there is an incoming message. Nope. 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 Okay. Anyway, so why can't I hear Destiny?
Was basically talking about how he wants journalism to be done the right way. He wants reporting to be
12 minutes.
I want to have a little chat about the Russia stuff a little bit more, kind of some tangential notes, because I've been doing a video about this stuff and I was looking into it. What do you know about Benny Johnson?
Crazy, absolutely insane propagandist. Wouldn't surprise me if he was being paid by somebody, but could also just be incredibly stupid.
No, these people are not getting paid. They are getting paid, but they're not getting paid to say something. They're getting paid to spread, to help them spread what they're saying. They're not getting paid to say, they're getting paid to spread. Putin is paying Tim Pool, so that Tim Pool now has another $1 million that he can spread, that so that Tim Pool can spread his message, right? Because Tim Pool always takes every penny and reinvests it in his own business. So Tim Pool will take the money and will invest it to spread his own message, and his own message is Putin's message. It's the same message. Tim Pool and Putin agree on everything, basically. Tim Pool at this point is an extremist, is an extreme right winger. And there's plenty of extreme right wingers who are, and so is Putin. It's just that there is a complete agreement between these two. Putin doesn't need to pay Tim Pool so that Tim Pool will agree with Putin. That's not how it needs. It doesn't need to work like that. But Destiny doesn't understand it. That Destiny thinks that people are getting paid to say instead of getting paid to spread. He doesn't understand that.
Well, no,
So do you know-
Sorry, not stupid. He is intentionally malicious. Sorry, go ahead.
Do you know anything about
No one is intentionally malicious. No one. Not even Hitler was intentionally malicious. Hitler gave his life for what he believed. So that's not intentionally malicious.
his history?
No, I don't actually at all. For my impression, he just started to pop up. I've seen him on peers, or I think I've debated him on peers a couple times, but I don't know anything about his past. He could be an established figure, and I just wouldn't know. I don't know. Why? What about it?
Okay. So I was looking into his stuff. I browsed around his Wikipedia a bit. I browsed around some other websites, and I found out that he actually used to work at BuzzFeed, which is pretty interesting. He worked there, I believe, from 2012 to 2014.
Okay.
And he was, writing articles there, which is, kind of a weird place to work, just retrospectively, obviously, but that doesn't necessarily.
Let me just change so that we get people to join us instead of boring stuff. Let's just say that I'm doing quantum physics. Is this how you spell physics? I don't know how to spell physics. Quantum physics, spin, Bell's theorem, or inequality, whatever. That's still bothering me. And Zabine said she doesn't see a problem with that, so I need to figure that out. That's still I'm still trying to figure that out. And also chilling and reacting to YouTube. So everything all at once. All at once.
Really mean anything. I mean,
Sure.
people can work
Oh, I
somewhere
will
despite not
say
agreeing with the politics.
One thing I'll say, if this ever comes up in your video, just a minor aside, there was a brief moment in time where BuzzFeed was going to make like a genuine foray into the political world, and they were actually doing a surprisingly good job, and then they gave up after a year. I don't know why, but just as a heads up on that.
Right.
Okay.
Well, maybe when
It's not just that, it's also there's politicians who do the right thing, but very quickly you discover that you don't get anywhere by doing the right thing. Unfortunately, you have to be terrible to make any progress in this world, apparently. You can't just do the right thing. Unfortunately. I mean, Milei in Argentina is doing the right thing, and he is making progress, but I don't know if the people will appreciate what he's doing for them, because it's so easy to manipulate the masses that I just don't know.
one of the reasons they gave up is because of the reason Benny was fired. I have an article here from Politico, and I was curious to have you take a look at this. It's pretty interesting. This is not the only allegation within this realm that's been made about Benny, but it is interesting just because, like, I was looking through the Tenet Media promotional video, and Benny was basically talking about how he, he wants journalism to be done the right way. He wants reporting to be done the right way.
Yeah.
And this guy has a history of
hysterectomy. Anyway. Num, 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 num. What else? Demonstrating quantum. Yeah, I want to go back to the quantum. This was fascinating to see the Stern-Gerlach original experiment, but still, it's good to see the original experiment. This is interesting. Yeah, I need to watch this, but he says you first need to watch 6.
Hydrogen orbitals per energy level. 1, 4.
So he's
Welcome to Quantum Mechanics 8, Spin. In many ways, this video is about the number 2, how it crops up in atomic behavior, and the seemingly impossible explanation for this. We've already seen in video 6 that the number of hydrogen orbitals.
So there is a video 6. Who is this guy? His name is Via Science. So I don't know where is his 6. This is spin 2. Maybe we'll. Oh, but maybe it's a playlist. Spin 2.
Let's now see how electron
9.
spin explains why.
9.
Welcome to the 9th video in this series on quantum mechanics, where we'll discuss photon spin and the quantum paradox known
9b. 10a.
We've seen that a photon
9c. Yeah, this is. What is this? Is this the list?
one of the first, and in many ways, the standard point of view is the so-called Copenhagen interpretation,
What is
a
this?
term coined by Werner Heisenberg, who worked with Niels Bohr in the latter's Copenhagen.
Shut up. I don't know. I mean, how can I don't know how to use YouTube. Does YouTube know how to use YouTube? How do you do this? How do you I want to go to the previous video. Like, the guy numbered his videos. How difficult can it be for YouTube to let me watch the previous one? And what is this? This is, it doesn't even tell. Oh, watch later. Add to queue. Oh, add to queue. Okay. 9 years ago. Wow. Oh, this is the playlist. Okay. Thank God. Birth of Quantum. Might be worth it to watch it in order. It's a little bit daunting, especially Dirac. This is good. Quantum mechanics chemistry. Maybe we're ready to watch it from the beginning. In the beginning. Oh,
YouTube video series on. Welcome to Quantum Mechanics 1, Birth of the Quantum, the first installment of this YouTube video series on quantum mechanics. The word quantum might bring to mind exotic phenomena, such as particles having wave properties, electron clouds and atoms, esoteric particles and processes associated with particle accelerators, and spooky science fictionist scenarios like quantum teleportation. But if you want to understand why quantum theory is necessary, you need look no further than an incandescent light bulb. Near the end of the 19th century, the electric light was revolutionizing society, based on the seemingly simple process of using electric current to heat a filament until it glowed. The underlying physics was actually
okay. So far, I'm following.
not well understood. Most of the energy was emitted outside the visible range of wavelengths, severely limiting efficiency. Most of the until it glowed. The underlying physics was actually not well understood. Most of the energy was emitted outside.
Why is the underlying physics not well understood? I mean, you're heating it, so the molecules are vibrating. I would say, okay, yeah, you're right. It's actually not. I wouldn't know how to deal with it. Like I would say, the electron goes bobs up and down. Somehow it goes up in its orbit, in its orbital. What I know about the orbital, they didn't know about the orbit. I don't know what they knew. Did they even? What year? What year are we talking about? So this is what year is this?
The underlying physics was the process of using electric light was revolutionizing society. Light bulb. Near the end of the 19th century, the electric
the
light was
end.
revolutionizing society based on the seemingly simple process
Near the end of the 19th century, he said. So it's about 19th century. Yeah, so it's about 1900. So close to 1900. So close to 1900, they were trying to figure this out.
of using electric current to heat a filament until it glowed. The underlying physics was actually not well understood.
And they used to use so many filaments. Today we have new light bulbs that also use multiple filaments, but now it's LED filaments. So it barely heats up and it spreads incredible amount of light. What's this? President Sunday. Okay.
Most of the energy was emitted outside the visible range of wavelengths, severely limiting efficiency. The general problem of understanding
Right. It was basically like glowing, but also heating up. So that's a waste. They wanted to avoid, I guess, the heat. Temperature and light intensity versus wavelength. Temperature, light intensity versus wavelength. Right. There's three parameters. So as you increase the temperature, the light intensity increases, but also the wavelength decreases. So it begins as reddish and it ends up as white or blue or something.
the relation between temperature and the variation of light intensity was emitted outside the visible range of wavelengths, severely limiting efficiency. The general problem of understanding the relation between temperature and the variation of light intensity with wavelength is what gave birth to quantum theory. The hero of our story.
Yeah, the hero is Max Planck, 1858 to 1947. So he died at the end, like after World War II ended. I think the war ended in 1945. So he survived the war.
Story is Max Planck.
He wasn't pro-Nazi, he was pro-Germany.
Who began studying physics in 1874. This was after being advised against this by a physics professor on the grounds that, quote, in this field, almost everything is already discovered, and all that remains is to fill a few holes. A premature statement, if ever there was one. Planck's doctoral thesis concerned thermodynamics, the study of the relationship between heat, temperature, and the properties of mechanical systems.
It's very interesting someone would say this. I mean, they barely had any knowledge compared to what we have today. And today we have so many questions. It's like the cavemen. The cavemen didn't know anything.
In 1894, he was
he was an expert in thermodynamics.
commissioned to research how to obtain the most output from a light bulb for a given input of electrical power. As reflected in the physics professor's advice, many people at the end of the 19th century thought physics was largely complete. Three broad areas of phenomena had been successfully described. Mechanics explained such things as orbital motion, the solar system, the behavior of structures and machinery, acoustics, fluids, hydraulics, and aerodynamics. Thermodynamics and statistical mechanics explain such things as the relation between heat flow, temperature, pressure, and volume, steam.
This is very interesting. Carnot, again, a Frenchman. The French contributed a lot. There's something interesting about the French. And what is this? Is this a steam engine?
and gas engines, refrigeration, irreversible processes,
I think the refrigeration was invented by Einstein.
and the relation between microscopic molecular dynamics and these macroscopic phenomena. Finally, electromagnetics explain the wave nature of light, other types of radiation, such as radio waves, and the laws governing electric power generation, transmission, and utilization by electric motors. It's the interplay of the last two areas where the need for quantum theory became apparent. To understand that, we need to start by looking at how statistical mechanics explain the distribution of energy among a collection of molecules at a given temperature. As an example, let's consider the behavior of gas molecules in a box.
So this would be the Maxwell-Boltzmann distribution, probably, or something.
There are about 30 billion.
This is the distribution of wealth, or wealth inequality, which is a natural phenomenon.
Molecules in a cubic centimeter of gas. We're going to look at a computer simulation of 10 ideal billiard balls on an ideal billiard table as a very simple model of our gas.
Oh, they're going to be bouncing against each other? I thought they don't interact.
Yes. We'll start with all the balls at rest, and then we'll set one in motion and see what happens. As time goes on, collisions transfer energy between balls. The kinetic energy that was originally contained in a single ball is eventually spread among all the balls, but not equally. Some balls are moving faster than others. In fact, the speed of each ball changes every time it suffers a collision. Let's look at this more closely by following the history of a single ball, which we color black. The velocity can change dramatically with each collision. It seems quite hopeless to come up with an accurate description of any given ball's motion. And if this 10-ball scenario is intractable, then describing a gas with billions of molecules is laughable. Or maybe not. In the 19th century, physicists, most notably Ludwig Boltzmann, realized that while it was impossible to keep track of the trajectory of each molecule, it was possible.
So Boltzmann ended his own life. Like, I don't know, man. A lot of people suffered from depression, especially in those days. Like, we have this feeling that their lives were better but no, a lot of them ended their lives. Like, all of Mark's daughters ended their own lives. They all went into mental asylums. Everybody was so screwed up in those days.
To make definite.
Like, today, we're much more normal than they used to be. I would say. I think maybe they were a very closed society. I don't know.
Statements about the statistics of those trajectories. The resulting analysis, called statistical mechanics, turns out to be very powerful and played a critical role in the development of quantum mechanics. The key is to find solvable problems that can be used to model the behavior of a complex physical system. To see how this works, consider a number of boxes and a number of balls.
Okay, so we left alone the previous thought experiment. We never came up with an answer to that, but we will come back to it. That will be the answer. I mean, the Boltzmann-Maxwell distribution is identical, basically, to the ultraviolet, catastrophe. So, the black body radiation. So we should be able to come back to it and be able to explain it somehow. Yeah, okay, so the next thought experiment.
To see how this works, consider a number of boxes and a number of balls distributed among those boxes. Here we start with 3 balls in each of 10 boxes. Now, randomly choose a box, and if it's not empty, move one of its balls to another randomly chosen box. Then randomly choose another box and move one of its balls, and so on. After doing this many, many times, is there anything you can say about the distribution of the balls among the boxes? Here we'll investigate this by simulating 1,000 boxes, each initially containing 10 balls.
So my intuition is that it should be a flat distribution. It should be a uniform distribution. That's my intuition. But I don't know.
Performing 1 million of the random ball transfers, we end up with widely varying numbers of balls per box. Now comes the statistics part. For any number of balls,
this is very interesting. So it's definitely not uniform. There is a certain fluctuation, but there's 1,000 with how many each? I guess there was like 10 each or something. How much was there in the beginning? Yeah, 10. So 1,000 with 10 each.
Performing 1 million of the random ball transfers, we end up with
Million.
widely varying numbers of
So after 1 million, you have basically the this one is at 45, which is 500% of the original. And you have right next to it one that is almost completely or maybe completely empty. There's a few, I think there's two of them that are empty here, a single one empty here, and these are two right next to each other that are empty. I think these are two that are empty next to each other because this is like a thinner line. A very interesting distribution. Interesting. So spikes going both ways. It's basically noise. It's basically static, but very severe static. Okay.
balls per box. Now comes the statistics part. For any number of balls per box, for example, the red line here corresponds to 15, we can go through and count how many boxes have that many balls. We can do this for every possible number and display the results on a histogram where the number of balls per box is shown on the horizontal axis.
Okay. So this is balls per box and the fraction of the boxes. I would show the percent, but it's, I guess, the same. So it says 0. 0 have 0. That's what it looks like, which is impossible because I saw that that's not true. But this is very interesting. So there's a lot with very few and very few with a lot. So you could say it's very similar to the wealth distribution. This is nature. This is just random. Because of randomness, you get very few with a lot, and a lot with very few. This is just by sheer randomness. Wow. Just a random process rewards very few with a lot of not just money, a lot of power. Very few randomly have a lot of power. Forget about money. This could be beauty. This could be health. It's not just money. I mean, people are quick to want to redistribute money. Why don't you redistribute health? Cut off, like if there's healthy people, just cut off their limbs, make them, right? You want to equalize, so do that. But people are very quick to spread money. Oh, take his stuff away. Very interesting.
And the fraction
But the question is there any with 0? Because okay.
of boxes with that many balls on the vertical axis. For the 15 balls case, we see that the fraction is about 0.03 or 3% of the boxes. Running more simulations, we find similar histograms. These histograms tell us that a box is much more likely to contain a small number of balls than a large number. Now, the nice thing about statistics is that the more objects you have, the more precise the statistics are. In the limit of a very large number of boxes and balls, you can solve for these statistics with pencil and paper, and you get this red curve. Here's the result. In the limit of a large number of boxes, n, and a large average number of balls per box, m, the probability that a given box will contain little n balls is 1 over m times e to the minus n over m.
Okay. Is he going to derive it? Is this probability or statistics? I'm trying to think. This is it probability or is it this? I would say this is probability, right? The probability. So this is the probability of any number. So whatever number you want, it's 1 over m. What is m? In the limit of a large number of boxes n and a large average number of balls per box m. So this is the balls per box. This is the ratio of boxes to number of balls per box. Fascinating. Fascinating. So, for example, the more boxes you have. Anyway, this is really interesting. It would be interesting to see a derivation.
A decreasing exponential distribution.
Yes, that's what important. The angle brackets denote an average. What? So n equals m, the average of the number of boxes. I don't get it. What do you mean the average?
Again, the average number of balls per box is m. Okay, so
The average number. The average number of balls per box is m. Well, that is the original number, so that has to be the final number, right? That makes sense.
what? Well, now we'll make an analogy to our statistical mechanics problem. Decreasing exponential distribution. Again, the average number of balls per box is m. Okay, so what? Well, now we'll make an analogy to our statistical mechanics problem. Assume each ball represents a chunk of energy denoted by Greek letter epsilon.
So now we're going to go back to the billiard balls in the first example. To where is that? To this one. Okay.
Problem. Assume each ball represents a chunk of energy denoted by Greek letter epsilon, and the boxes represent anything.
Okay, so the epsilon, why is he changing these? He should name this capital M. Each ball represents a chunk of energy. So energy is what is being distributed. That's like the number of balls, not little, but big N.
That can contain energy, the molecules in our case. The process of randomly passing balls between boxes represents the random
Oh, this is molecules, okay.
exchange of energy between molecules. The balls per box distribution should therefore represent the energy per molecule distribution. The average energy per molecule.
So distributing the exchange, right? So the model that we built, so this should work also. This should be identical for the molecules bouncing around. So the average energy, what is capital M? Did he say?
Represent the energy per molecule distribution. The average energy per molecule is m times epsilon.
What is M?
The energy of any particular particle is
M in the previous problem, in the limit of a large number of boxes, you should like separate, like say each variable separately. So the number of boxes is n. Average number of balls per box is capital M. So this is the average energy. M is the average energy? I don't know what M is. I mean, is Assume each ball. Oh, no, no, no. He's still. Okay, I get it. He's still in the second example. He is still in this example. So in this example, he says instead of exchanging location, let's exchange energy. Isn't this completely different? So the average energy is the number of balls per box. Number of balls per box. Okay. So this is, in our case, it's 10 balls per box originally. Times, assume each ball represents a chunk of energy, epsilon. Each ball represents, I don't get it. So the average, okay. So the average energy, what is the average energy? Well, just take the number of balls per box. So in our case, it was 10. Assume each ball represents a chunk of energy. Is this the average? What is epsilon? And it's a variable? What is it? The average energy of what? Of each ball of what? The average energy. Well, it wouldn't make any sense to talk about the average energy of the system. So let's see, what did he define it as? I wish he would write out the definitions.
For represent the energy per molecule distribution. The average energy per molecule is m.
Okay. This doesn't make any sense because this is the average energy. This is the energy per molecule. This is the actual energy per molecule. I assume each ball represents a chunk of energy epsilon. This is the actual. So I would say this is. Nothing here makes any sense. What is he trying to say? This is the number of balls in a box. So it's 10. There's 10 balls in a box. This is some actual number? I don't get it. This is like a box. This is like the average energy of a box? Is this what he's trying to say?
The energy per molecule distribution.
Each box is a molecule? What is... Assume each ball represents a chunk of energy. Oh. Oh my god. This is going to be a long one.
Now we'll make an analogy to our statistical mechanics problem.
It's basically impossible to understand him. If this is the way he's going to teach this course, then I quit now. This is going to be impossible. There's way too many. He's skipping way too many steps. Like he's expecting me to read his mind. So if you're a mind reader, this would be a good course. Probably still the best introduction. Physics graduate here. Don't think I was ever taught. Well, so if this is for physics graduates, then I guess it's fine. I've watched a number of these science quantum videos and I feel immensely grateful. This series is great. Yeah, but this is survival bias. The people that just watched it and quit, they just quit. Please, and we don't even know how many downvotes he has. I don't have that feature. Wait, I don't even know how many likes he has. Can I know how many likes he has? I can't know anything. This is like one of the most important features of this system. And they took it away from us. For no apparent reason. They said we need to take it away from you because the comment section are hurting the feelings. Not the comment section. The comment section they didn't take away, because people usually lose their minds in the comment section. No, they took away the dislike button because it hurts the feelings of the creators. That's a lie, because the creators can still see the dislike counter. So that's a lie. So they lie to us. So why did they take it away? Terrible. Anyway, I've watched this. Everybody loves it. Please don't stop. These videos are very so happy. Really great course. Classically, the energy of a single mode wave does not depend on frequency. Okay, great. We'll cover quantum healing of atoms. When an atom that is troubled by too much energy and is healed by radiating some away. Mechanical objects are composed of a finite. Okay. Where was this when I studied physics? Your videos are great. Maybe as like as an added material. Building intuition. Why do we get exponential distribution in the random shuffling? The exponential, that's easy. Why it's simply not average? What do you mean? He ran a simulation. In each box over time, as that seems to be more attaining equilibrium in more probable state after a long time. It looks like over a long time, most of the boxes are being emptied and only a handful being loaded till top. Why? 5 years ago. It's a good question, but that's just reality. You might as well ask anything. Like, I don't know. Like, you might as well ask why 1 + 1 = 2. It is a good. I mean, both are good questions. Both are good questions, but they're just as valid, I think, in my opinion. Very good presentation. Everybody's very happy. Let's go maybe. Oh, that's it. No? A little bit. There's only 100 comments. Let's go to the first ones. So about 100 per micron. See, these are actual questions. Yeah, he wants to actually see the how you get the formula. We have a mono. See, actual questions. In the beginning, people were asking actual questions. Can you give? This is not at the beginning. This is 5 years ago, 9 years ago, 8 years ago, 3 years ago. So he was still answering question 3 years ago. What is the value of E in the probability that the box will have? Okay. Using pencil and paper. This is a classic problem in probability theory. P of n is proportional to the number of ways you can distribute n, m minus n balls among n-1 boxes, assuming indistinguishable objects. Wow. Why the energy of any particular particle is n times epsilon. Yeah, yeah. Each ball represents a chunk of energy. This allows a continuous energy problem to be analyzed in terms of a discrete energy problem for which the math is easier. By letting, I don't think the math is easier when you have objects. The math is easier when you just use continuous calculus. By letting epsilon go to 0, the discrete problem transitions to the continuous problem. So I think this is the question we wanted to know. Each ball represents a chunk of energy. This allows it continuous, but he doesn't. The question is why the energy of a particular particle is n times epsilon. I don't know. Is this the question? So the total energy does depend on the frequency after all. I don't know. You multiply the right side of the equation. We didn't get there yet. I don't think so. But people used to have actual questions. You multiply the right side of the equation by 1, hence the right side. Well, this is, I don't think we're at 637 yet. I cannot make heads or tails out of that formula. Which one? You have some large sample of boxes n, where you know the total number of balls is 10 times n, and you're telling me if I randomly picked up a box, the most probable number of balls that would be in that box is 1, then the next most probable being 2 and 3 and so on. That just doesn't make any sense. Yeah, dude, the m is supposed to be a partition function and not the average number of balls. M is the average number of balls per box. In this simulation, m equals 10. Yeah, but like people are having a hard time. Like if this was class, he would redo this lecture. Like the next time he would teach, he would make sure he explains this. Okay, and what's the explanation in classical physics for the energy of a wave to be dependent only? Okay. I don't understand whether classical theory fails to explain the amount of energy irradiated from the light bulb. Yeah. Same guy. This might sound stupid, but what do I need to learn to understand the math in this video? I currently only have basic math knowledge, and I'm looking to study the prerequisites of quantum mechanics. For this particular video, you would need a review of equations and train yourself in simplifying rational expressions. If I may, I would recommend using Khan Academy website. Free and nonprofit educational, just like Via Science. That's what I did before I came back here. Oh. I think I'm starting to understand this, but if classical physics fails to explain the light bulb, shouldn't it fail to explain the vibrating violin string as well? As far as I know, classical physics has no problem explaining why the intensity of sound from a vibrating string is less than infinite. By the way, thank you. This is good. It's the same guy. This guy knows his stuff. You said balls. I have just heard of the new variation of the dual slit experiment where the observer can delay deciding to observe. But isn't the UV catastrophe the prediction by classical physics that the energy, same guy, this guy's asking a lot of questions, that the energy irradiated would be infinite because of an infinite frequency. But the bulb couldn't possibly emit. 1 second, we have a message. Oh, blush. Let me just make sure. Okay. I'm streaming. Anyway, science media. If this series is anything like your series on GR, it should be great. Oh, this is the first guy 12 years ago. They're really informative. I especially like the visualizations. One second. Again, R.A. Castillo from 11 years got it. So the UV catastrophe, okay, we didn't get there yet. So 11 years ago, we couldn't reply on YouTube. We could only post comments. There was no reply button. YouTube was terrible and still pretty much is, technologically speaking. Like there's basically no indication when somebody answers my comment. I usually I never know this. Years can go by and then I notice a comment somebody made on my comment. More the temperature, more the energy. And then okay, I have a hard time building intuition. Okay. So I think so there's very few comments. There's basically very few comments. So we are at 558 and I'm trying to understand this equation and it's basically impossible. I don't know what to do. And this is just the beginning of the course. And already he's skipping steps.
Assume each ball represents a chunk of energy to know.
So balls represent chunks of energy, right? We're talking about this example. So balls represent chunks of energy. Assume each ball represents a chunk of, right? This is a separate discussion. So once we discussed how it gets redistributed, now we know that it gets redistributed according to like a natural logarithm. That's fine. A decreasing natural logarithm. So now the question is, let's go back to this question. Assume each ball represents a chunk of energy. Yeah.
By Greek letter epsilon, and the box.
So each ball is a chunk of energy epsilon. So epsilon is actually a constant. A ball is epsilon. Epsilon is not a variable. It doesn't vary. It's a chunk of energy, okay?
Boxes represent anything that can contain energy.
Okay, and a box represents anything that can contain energy, like an atom. So a box is actually an atom or a molecule, right? Because we're trying to analyze why a glowing filament or why a heated filament glows, why anything that is heated glows. Why do things glow when they are heated? This is the question that we're trying to answer. So I don't know why he's going. I don't understand where he's taking this discussion. He should say, let's think about a heated filament. Let's think about it. Like, let's go back to the way Max Planck thought about it. So what was Max Planck thinking? Why are you going to these boxes and stuff? Like, you're not made, there's no connection. I'm trying to see the connection. This is pedagogically a mistake. I feel disconnected. I don't see the connection between the film, right? You asked the question, why is the heated filament glowing? Why is a light bulb glowing? Why do things glow? That's the question. So how is this related to this question? You can't teach like this. This is not a proper way to teach. I don't know where you're taking us. There's no motivation to follow you. You have to motivate the student, not motivate like a pep talk, like motivate like whatever every sentence you utter, there has to be a motivation, meaning it has to be relevant, it has to be answering a previous statement or questioning a previous, it has to be relevant to something previous. That is like this is terrible. Anyway, let's think about it. So he says these are basically atoms. So each box is an atom, and each box has, so each atom has energy. So what he's trying to say is that, like, you could say it's I would even say it's the velocity. Right, so we were trying to analyze the velocity. Now I'm beginning to understand why he brought us here. So we were trying to understand, remember how we came to this point? We actually started here with the bouncing billiard balls. So we were with the bouncing billiard balls, and we wanted to get the distribution of energy, or distribution of velocity, which is the same with these billiard balls. So in order to do that, he started with the redistribution of balls. And now he's going back to the redistribution. He's saying, well, let's assume it's energy. You don't even have to say that. Let's assume it's a chunk of velocity. So let's say it's velocity, right? Because when they bounce, they exchange velocity. So each ball, this is confusing because these balls look like the balls from before, but now the balls are the chunks of velocity, where before the balls were the atoms. Now the boxes are the atoms. Talk about confusing the students. Jesus Christ. No. This is going to be thoroughly hopeless. If this is the way people teach, then we're hopeless. This is hopeless. This is introduction to quantum mechanics. This is going to be completely hopeless. Absolutely hopeless. Anyway, so each ball is a chunk of velocity, chunk of energy, which is a chunk of velocity. And basically, when a ball switches boxes, that's basically the interaction of two atoms. Each box is an atom. Each box is a billiard ball, believe it or not. I'm sorry. So whenever two billiard balls bounce against each other, they exchange velocity. They exchange momentum. So that's akin to this example where two boxes exchange a ball, exchange epsilon. This is so confusing. Why would you even say epsilon? Jesus Christ. So confusing.
The molecules in our case. The process of randomly passing balls between boxes represents the random exchange of energy between molecules. The balls per box distribution should therefore represent the energy per molecule distribution. The average energy per molecule is m times epsilon.
Okay, now we're ready to maybe understand this equation. The average energy of box, this is the average energy of a box, is the number of balls, the original number of balls per box times the constant energy that each ball represents. Now this is very simple. So this is absolutely the worst way to explain. I mean, this is something so simple and so impossible to understand in the way he's teaching it, unfortunately. Unfortunately. So the average energy of a box, he might as well write it in plain English. The average energy of a box is equal to the average number of balls per box times the energy of each ball, which is a constant. Now it's very simple.
The energy of any particular particle is little m.
The energy of any particular box, see, he's switching now between particle, molecule, box. Absolutely terrible. This is the actual energy of a box, of an actual box. Well, how many balls does it actually have? So, look, he's using little n, where before he also had little n. What is little n before? That is, given box will contain n balls. But capital N is the number of boxes. Wow. Like can you, like, he was thinking, how can I confuse the students even more? Oh, so let's reuse little n, big N to denote completely different things. Yeah, that will confuse them, because quantum mechanics is supposed to be even more confusing. Jesus Christ. So the actual, might as well write this in English as well. Like, somebody needs to, like, I wish we could make videos about videos. Well, that's what I'm doing, I guess. So the actual, yeah, but it's impossible to link. They used to have a respond button, a literal respond button, and they removed it. There used to be a respond button. Like, do you know that YouTube started as a dating site and Facebook started as a face rating site for girls? Yeah. And YouTube initially, Google initially, they tried to create their own YouTube and they just couldn't get it technologically. They couldn't figure it out technologically. Anyway, so the actual energy of a box, just keep talking about boxes, is the actual number of balls times the energy per ball, which is a constant.
N times epsilon. To find the probability that a molecule will have an energy E,
It's not a molecule, it's a box. Stop saying molecules. So the probability that a certain box, I guess, will have a specific energy level. This is a specific number, so you can say 1 or you can say 0. 0 energy chunks, meaning this box or the molecule is not moving, the billiard ball is not moving, that's 0 level. 1 is speed 1, 2 is speed 2, 3 is speed 3. So it's equal to epsilon, the actual, this is the constant energy that each chunk represents, over m, the average energy. This is, well, this is the number, the average number of chunks, and this is a chunk. So this is the energy, the chunk energy before it was 1. So now it's right. You could basically get rid of these chunks. As you can see, you can get rid of these chunks. It's it's epsilon over epsilon, epsilon over epsilon. You might, it shows up here. How? Epsilon by epsilon, epsilon. How? Why should it show up here? Why is epsilon here? Because he changed the definition. Oh my God. Okay, whatever. But he shouldn't have done this. He should have first represented it with this. And he should have said, it doesn't matter, whatever. So this is the probability that any the probability that right, the probability ends up being a percentile or a proportion, a ratio out of 1, part of 1. That's the definition of a probability. What is the probability? Like, what percentile? Like, how many of the boxes will end up with a certain n epsilon? Epsilon is meaningless. You can get rid of it. You might as well re-express this question exactly as before, right? We haven't really changed this. This still applies. He's just adding now that there is epsilon energy, that each ball represents epsilon energy. Before, he didn't discuss anything about the ball. Now he's saying the ball actually has a constant value. And then there's this expression, which is an average energy. So he wants to plug in the average energy and the total energy. Because these are calculable. Because we don't know the average energy per atom or per billiard ball. We don't care about that. But we do know the total energy of the system. We do know the average energy of a molecule. Anyway, so basically he took the original equation and he just added epsilons after we figured these values out. So m epsilon, we discovered, is the average energy of a molecule, or a billiard ball. So this is the average energy of a billiard ball. And this will end up being Planck's constant. This is the minimal energy. Oh, that's interesting. This is the minimal energy that can be exchanged between molecules, between atoms in the quantum world. So you multiply by, okay, and then E, and then, can you hear me? Multiply by, okay, and then E. Yeah. Plus there's somebody watching. Who's watching? Who is watching? No one is allowed to watch. You're not allowed to watch. I disallow it. Anyway, so this is, so we're just multiplying by 1, by epsilon over epsilon. And epsilon, we discovered, is the total energy of a box. Is the actual energy of any specific molecule. Well, we don't know that. This is the actual energy of that molecule, right? When we're asking what's the probability that a certain box will have this energy level? Well, right, he might as well have said n epsilon is E. So what's the probability of E? I wonder why he didn't say that. This is n. Now he's saying n epsilon. It's just E. So anyway, so n, I mean, he's just multiplying by 1. He's just multiplying by 1. So, but why is this the probability? Why is this the probability of what he's asking? This is the probability that any box will end up with this number of balls per that box. What's the probability that a certain box will end up with this number, with 3 balls per box? What's the probability? To plug it in and get the probability, which is the proportion. It's 3%, 5%. 5 out of 100 will have that number. Okay, what's the probability that any box will end up with this energy? Well, it's just that number multiply by the energy. Right? What is the probability that any box will end up with this number of balls? This is the probability that that box will end up with that number of balls. If you multiply by this by epsilon, this number by epsilon, that's not correct. You don't want to multiply this by epsilon. So epsilon doesn't mean anything. Epsilon doesn't influence the equation. So you could have said, I mean, once you have defined, this is so complicated and he doesn't explain it. He's like, yeah, you don't need me to explain this. This is obvious. Yeah, this is completely obvious. Everything here is totally obvious, of course. I don't know. I mean, maybe right after I finished a course in probability and statistics, if I would maybe have this discussion, it would make more sense. I don't know. I don't know. I don't even know if that's true. So, oh my God, I remember the days when I used to go to school. Oh my God. Those were amazing days, amazing, both positive and negative. Anyway, so epsilon, anyway, it's very difficult to understand how he's doing this trick. So we defined m epsilon, we discovered that m epsilon is the average energy of any atom. So this is the average energy of any atom. This is the minimal chunk of energy that can be exchanged between atoms. This is n epsilon. This is right. We're asking what is the probability that any atom will have this level of energy, n times the minimal chunk of energy that can be exchanged between atoms, basically Planck's constant. So what's the probability of a certain energy level that any atom, pick an atom randomly, what's the probability that it will have this energy level? N epsilon. So n epsilon is the actual energy of that that we're looking at. Well, that energy, that E, and again, m epsilon is the average. Okay. Very, very confusing. Very confusing. 5 people are watching. Jesus.
We multiply in two places by epsilon over epsilon, which is just 1.
Mm-hmm. So we multiply epsilon by epsilon, which is 1. So we're allowed to multiply by 1. We're allowed to multiply by 1. And we're getting this expression.
And identify the expressions for energy E and average energy. Now, temperature is a measure of average energy.
Okay. So this is the average energy of an atom, of a box, of a ball. No, not of a ball. A ball is epsilon. The average energy of an atom is equal to the temperature times a constant. Right. So you would expect that the average energy of any particle, let's say even a billiard ball, well, billiard ball doesn't have temperature, but you'd expect, right? So as the temperature rises, you're basically raising the average energy of a particle. Now you have to do dimensional analysis. That's one thing I learned over the last, like I watched it the other day. Like dimensional analysis is so powerful. Just look at the dimensions. So temperature is just degrees, like Celsius or Kelvin. And what is energy? Energy is joules. It's like newtons times meters. So this K has to deal with it. But there's no Celsius here. So you need to this K needs to divide out the Celsius. So this K needs to be in terms of newtons meters, which is I think joules. So K needs to be joules per degree.
Energy per molecule. And we write the average energy per molecule as a constant K times temperature T. K is called Boltzmann's constant.
It's a misnomer. So Kathy loves physics and electricity and history, whatever, physics and history. So she discovered that it has nothing to do with Boltzmann, absolutely nothing to do with Boltzmann. It happens to be that Boltzmann is relevant in the Boltzmann-Maxwell distribution, but this might maybe this is Boltzmann-Maxwell distribution. I'm not even sure. But this K We'll see. Anyway, you can look at her video where she explains it. It's on this K is on Boltzmann's grave as Boltzmann's equation or something, but it's not Boltzmann. It's totally Max Planck. Nothing to do with Boltzmann whatsoever. She proves it. She proves a lot of things. She proves Tesla was a complete idiot. She proves it. Like she goes through his original writings. You see that like it's total nonsense. The guy was a Looney Tune.
Finally, we let our chunk of energy, epsilon, shrink to infinitesimally small. We'll call it
Mm-hmm. It becomes dE, where E. Why would you say? Yeah, okay, whatever. Because you can't say D with this E. But why is it DE? Why capital E? I mean, E is the actual energy of a box, right? There is a certain box that has a certain energy. The energy of a certain box, of a certain molecule, is the number of chunks of energy in that molecule times the value of a chunk of energy. So I don't know why you would say epsilon goes to dE. Anyway, as we predicted, K is joules per Kelvin.
dE, the differential of energy. This describes a continuous exchange
Okay. So it's a so the chunk of energy becomes a differential of energy. Okay.
of energy among the particles. The resulting probability that a molecule will have an energy
Okay. The resulting probability that a molecule will have energy between E and E plus dE. That's interesting. So between E and E plus dE is 1 over KT. Right? So we ended up here. I mean, he never derived this equation. He should have derived it. Like, take a minute to derive it. Okay, let me just see the battery status. 70%. 86%. All right. So let me check messages. Oh my God. Absolutely terrible. Okay, so he's saying that. So we got up to here. Now he's saying the average energy, which we said before is this, well, it's also this. I don't know where he got this from. So he's just dropping things on our heads as if he has a basis for it. Why would you say that the energy is linearly related? How do you know this? That the energy is linearly related to the temperature. Where do you get this from? Let me look this up. Let me ask maybe ChatGPT. energy equals what? KT. A simplified expression is a simplified expression used in statistical mechanics and thermodynamics to describe the average energy associated with thermal motion in a system. Here's a breakdown of the terms. E is the average thermal energy of a particle. K is Boltzmann's constant. The Boltzmann constant, which relates the average kinetic energy of particles. This is Planck invented this. Energy of particles in a gas with temperature. Its value is approximately 1.38 10 to the okay. T is the absolute temperature. This equation is often used to approximate the thermal energy in systems where temperature plays a key role, such as in ideal gases. Wait, PV equals nRT has nothing to do with that, where each degree of freedom contributes energy proportional to KT. So degree of freedom is actually really complex. It's so complex. Context. Equipartition theorem. In many systems, particularly gases, the equipartition theorem states that each degree of freedom, translational, rotational, or vibrational, contributes 1/2 kT of energy to the total energy of the system. Why? Why 1/2 kT? For monatomic gases, where particles move in 3 dimensions, the average kinetic energy of a particle is 3/2 kT, representing 3 degrees of freedom movement along XYZ application. Thermal energy. Oh my God. Would you like a specific example of how? No, I just want to get there. Can you derive it? Please derive E equals KT. It's going to say the same. That's it. It's repeating everything. Maybe a little bit more information this time. Oh, there it is. E equals KT. This derivation shows the relation between temperature and energy, and the approximation E equals KT is useful in contexts where this precision isn't crucial, but the thermal energy scale is. In many contexts, a simplified version of this is used. For 3 translational degrees of freedom, total average kinetic energy per particle is 3/2 kT. Equipartition. So 1/2 kT is in any single direction. There's 3 directions, so it's 3/2 kT. Okay, but why would you say it's kT? The Boltzmann constant K sets the scale for this thermal energy, which allows us to estimate energy at room temperature. In semiconductor physics, thermal energy approximation. In many simple systems, particularly when discussing thermal energy in various kinds, is used an approximation for the average energy per particle. Why? Why? The equipartition theorem states that each degree of freedom contributes an average energy of 1/2. For monatomic gas, the kinetic energy is solely due to translation in 3 dimensions, XYZ axes, Hence, the total average kinetic energy per particle is the energy average per particle is 1/2 kT times 3/2 kT. That's not kT, that's 3/2 kT. In a system of particles at thermal equilibrium, the kinetic energy of particles is distributed according to Maxwell-Boltzmann. Right. That's what we saw before. The average kinetic energy of a single particle can be derived from the equipartition theorem. Equipartition just means if you basically random distribution, which states that each degree of freedom contributes an average energy of 1/2 kT, where K is Boltzmann constant. Maybe we should ask it to derive this, but that's not even going to help us because the answer is not 3/2 kT. The answer is kT. What do you mean it's simplified? What do you mean simplified? The equation is a simplified expression of what? What is the actual expression? Wait, what just happened? Simplified of what? What's the non-simple simplified form? No, it's just repeating itself. It's just repeating itself. If this is how we're going to learn quantum mechanics, then we can't learn quantum mechanics. This is impossible to learn this way. This cannot be done. This is absolutely impossible. I hand in my hat. You hand in your hat. I don't know what to say. So the average energy is kT. That's it. Deal with it. This is terrible. And I guess this is the Maxwell-Boltzmann distribution. Absolutely terrible. So the probability that any molecule will have the energy level between E and E plus dE, or just its energy will be E plus dE. I don't get it. Why do you need to say between E and E plus dE? Just say E plus dE. I don't know why he's saying that. Anyway, so average energy is kT, so he's plugging in kT here. E times, and then epsilon becomes dE, and E stays E, and average E becomes kT. 1 second. Ugh, my eyes. I'm tearing from happiness. I want to kill myself. This lecture is hopeless. This is a hopeless lecture. Oh my god. Oh my god. This is just hopeless. Hopeless. Oh. Anyway, so okay, so this is the equation.
E is 1 over kT times e to the minus e over kT. This is called the Boltzmann distribution.
Nothing to do with Boltzmann. This is totally Max Planck.
Statistical mechanics provided powerful explanations for phenomena arising from the interaction of many particles. It accounted for the relation between pressure, volume, and temperature of an ideal gas. It clarified the somewhat mysterious thermodynamic concepts of entropy. But when these ideas were applied to situations involving electromagnetics, a serious problem arose, the solution to which required a radical rethinking of the physics of the very small.
So hold on. Let me just repeat this statement. So he says this was good for thermodynamics in general. Let's hear this soliloquy again.
Over kT. This is called the Boltzmann distribution. Statistical mechanics provided powerful explanations for phenomena arising from the interaction of many particles. It accounted for the relation between pressure, volume, and temperature of an ideal gas.
So for an ideal gas, it was fine.
It clarified the somewhat mysterious thermodynamic concepts of entropy.
Okay, it helped with entropy and stuff. Okay.
But when these ideas were applied to situations involving electromagnetics, a serious
Electromagnetics. We didn't deal with electromagnetics. We're heating a filament and it's glowing. But the glowing is light, and light is electromagnetics. So as soon as light is involved, now we have a problem. Okay.
problem arose.
So, but everyone agrees that atoms are quantum objects, basically. Or do they? I don't know. So, as far as atoms are concerned, there is no issue. It was working fine. But when it came to electromagnetics, that's when we had a failure. But atoms are still very small. So it's not that we have a problem with quantum mechanics. We have problems in quantum mechanics. It's not that quantum mechanics, we cannot understand it. It's that in the world of the quantum, in the world of the very small, we have problems that we don't understand everything. Sometimes, because they didn't understand it, and then Max Planck came and he figured something, and then Einstein figured something, and slowly we're figuring things out very slowly. But it's not that we don't understand quantum mechanics. We don't understand the world of the small. Oops, oh my god, I hit my computer. We understand it, but we also have questions, But these questions are getting resolved very slowly, but getting resolved. So there's no need to panic and say, "Oh, this cannot be understood." Multiverse, reality's broken. Oh my god. Imagine a child learning 1+1 is 2 or something and is having a hard time and claiming reality's broken every time a child doesn't understand something. Oh, reality's broken. I don't understand rational numbers. Reality's broken. Imagine. Jesus Christ, what a crybaby. It's like today's scientists. It's not even today. It's since, I would say, Bohr. I don't want to blame anyone, but Bohr was a major power that, like, a major crybaby. Like, did he say we need to forget about conservation of momentum? Bohr. That's how you spell Bohr, or maybe Bohr. How do you spell Bohr? On Bohr on conservation of momentum. Niels Bohr contributed significantly to atomic physics, quantum mechanics, but his work didn't primarily focus on the concept of conservation of momentum. However, Bohr's model, I don't care about that. I mean, did he or did he not? Did Bohr say that we need to forget about conservation of momentum. No, Niels Bohr never suggested that we should forget about the conservation of momentum. In fact, conservation of momentum is fundamental. I saw a quote from him. Bohr did emphasize the classical concepts, including momentum, need to be understood differently when applied to quantum systems. Okay, what he actually, Bohr's contribution, classical physics like momentum are essential. They need to be applied carefully in quantum mechanics. For example, in the quantum realm, particles like electrons behave as both particles and waves. No, they don't. Their momentum is subject to probabilistic interpretation rather than deterministic classical view. I don't even know what that means. Complementary, Bohr introduced the idea that different aspects of quantum system, a quantum such as wave and particle behavior, are complementary and cannot observe both perfectly at the same time. What? In quantum mechanics, momentum and energy conservation remain fundamental principles. Misinterpretation. If anyone took Bohr's ideas to mean that principles like conservation of momentum should be forgotten, that would be a misinterpretation of his work. No, there is a quote. Show me the quote. No. You're not going to accuse me of misinterpreting. What is the quote? Is there a quote from how do you spell his name? Yeah, that's how you spell it. Bohr. Is there a quote from Bohr that says that we need to forget about conservation of momentum? There is no known quote from Niels Bohr. Forget about conservation. On the contrary, Bohr maintained fundamental. No. I saw a quote. I did see a quote. There is a quote. Let's ask Google. Let me take the question. Edit message. Okay, whatever. Copy. Paste. There is no direct quote from Niels Bohr. There's no direct quote. I saw a quote. 3 days ago. What did I look at it 3 days ago? Okay. Next time I see a quote, I need to remember it. Anyway, I have a message. Let me see. Okay, it's going to take a while for the message to come up. Let's see. Wow, she's hot. Very hot. Oh, she does yoga. Yeah, these chicks with the yoga pants. Mm-hmm. But they don't take care of their faces. They let the faces dry up. Let me think about it. I'll think about it. I'll get back to you. Okay. So, where are we? we're still watching this video, right? We haven't killed ourselves just yet. So we don't know. I have no idea how, like, why is the average energy equal to KT? Where is this from? Is this empirical? Let me Google it. E equals KT. Where is this? This guy. This guy. Why does it not remember? How difficult is it to remember? Anyway, so did I hear something? I think I heard something. That was weird. Weird. Okay. So KT, also known as KBT, is the product of the Boltzmann constant K or KB and the temperature T. This product is used in physics as a scale factor for energy values in molecular scale systems. Sometimes it is used as a unit of energy, as the rates and frequencies of many processes and phenomena depend not on their energy alone, but on the ratio of that energy and KT, that is on E over KT. See Arrhenius equation. Arrhenius. In physical chemistry, Arrhenius equation is a formula. Like I've seen this guy's name just way too much. The equation was proposed by Svante Arrhenius, 1889, based on the work of Dutch chemist Jacobus Henricus van 't Hoff, who had noted in 1884 that the van 't Hoff equation, anyway, Boltzmann factor. Statistical mechanics and mathematics. A Boltzmann distribution is a probability distribution of probability measure that gives a probability that a system will be in a certain state as a function of that state's energy and the temperature of the system. For a system in equilibrium in canonical ensemble, a statistical canonical ensemble is a statistical ensemble that represents the possible states of a mechanical system in thermal with a heat bath at a fixed, I don't know. The probability of the system being in state with, I have no idea what these guys are talking about. It's like KT energy. KT is the product. Like they're not even discussing E equals KT. What is going on here? I've never seen anything like this. Let's try YouTube. The most epic Israeli intel operation ever. The self-help lie I've seen ruin people's lives. That's incredible. That's worth a listen. 9-year-old mops floor with Olympic breakdancer Ray Gunn. But is it a boy or a girl? Okay, look, let it go. Ray Gunn. She won fair and square. What do you want? There were judges there. What do you want from her that she won? What? And where is this the 9-year-old? Where's the 9-year-old? That's pretty good. I mean, she has pretty. That's good. Yeah, Let's see the 9. Where's the 9-year-old?
Talent and skill. It's certainly a fact that she is delusional, but this may be
She's not delusional. There's judges. Are you? Is everyone out of their minds? Okay, but it's a combination. You win some, you lose some. You don't win everything.
extensively on this channel. I didn't plan on covering anything else until there was some new updates of Raygun embarrassing herself.
She did not embarrass herself. She won. What do you want?
Of a 9-year-old breakdancer, let's just say this kid could give physics a run for its money. Today we're going to be talking about Sui. She's a true prodigy, a breakdancing ninja warrior poet. At 9 years old, Sui is an Australian-Japanese breakdancer who clearly takes breakdancing very seriously. She's not just showing up people, she's mopping the floor with her opponents.
Sui.
Why is there no music?
Oh! Oh!
No music. Are you? Why is there no music?
Yeah, right on time.
Look, which one do I appreciate more? I appreciate more the little girl. This is for me. I agree, it's nonsense, but it's an Olympic sport, and there's judges, and you get rated on different things, and that's it. The judges like it. What do you want from me? What do you want from her? But why is there no music?
You can see in this footage the
Oh, he doesn't want to play the music because he doesn't want to get a strike.
Sui is all substance.
You get rated on different things. There's different metrics.
I think you are the best female breaker in Australia?
Well, I think my record speaks to that.
Her record speaks to that. What do you want from her? What do you want from her? Explain to me what you want from her. What did she do wrong?
Give it up, yo, shout out.
Like, people are out of their minds.
Breakdancer female that we have for Australia.
So you be ranked #1 and you didn't even place. And then you shouldn't have even been on the plane going to France in the first place.
But she was sent. What do you want from her?
Well, this is too much. I can't accept that ranking because
Who are you?
shit was trash. The shit was straight up trash.
But who are you?
Is there?
Her traditional and powerful technique is flawless. Her dedication is evident.
What do you mean traditional? Who decides? Anyway, this is a waste of time. Let's see any notifications. How did they do that? Electric Viking, Professor Tim. Okay. Oh, that's interesting. Anyway, Dave Bautista. What do you want? Like, people stop training and that's it. When they train, they look good. When they stop training, they look bad. Life. And then they die. You're going to judge their corpse too? Israel goes for final assault. I don't think so. Israel doesn't go for anything. Israel is a democracy, and as such, it's not going to do anything. It's going to poop its pants. Democracies are hopeless. In the long run, democracies are hopeless. Morning scene Beirut after Israel's strike kills Hezbollah commander. Middle East expert. Hezbollah's Arab foes relieved the terror group not as strong as assumed. Pay attention to how people treat pets. Interesting. Huge Olympic breakdancing ray gun update. Okay, forget it. Okay. Okay, let's get back to business. So E equals KT. Exponential growth and decay formula? Exponential growth and decay equals KT? No, E equals not E to the KT. E equals KT. Maybe Boltzmann? KT as benchmark? Boltzmann statistics for quantum mechanical systems? The Boltzmann factor? Boltzmann constant?
First of all, this guy, Ludwig Boltzmann, who was a genius, he lived in the late 1800s and early 1900s, and he was the father of modern atomic theory, one of the big proponents, early proponents that the world is made out of atoms and molecules. This sounds obvious to us now, but 120 years ago.
Yeah, let's continue here.
Let's talk about Boltzmann's constant. It's named after, first of all, this guy, Ludwig Boltzmann, who was a genius. He lived in the late 1800s and early 1900s, and he was the father of modern atomic theory, one of the big proponents, early proponents that the world is made out of atoms and molecules. This sounds obvious to us now, but 120 years ago, it was definitely not obvious, and some of the smartest people of his day vehemently disagreed with Boltzmann, and Boltzmann had to defend these ideas over and over. And what I mean by atomic theory is this. If you had a container of, say, anything, it could be a cube of metal, let's just say it's a gas. Let's say it's a container and it's full of air. Well, it feels like the air is continuous in here, or like the gold. If this was a cube of gold, the gold is continuous, but we know now, and Boltzmann knew, that it's really made out of atoms and molecules. That wasn't obvious 120 years ago because you can't see the atoms.
Wait, what?
The gold is agreed with Boltzmann, and Boltzmann had to defend these ideas over and over. And what I mean by atomic theory is this. If you had a container of, say, anything, it could be a cube of metal, let's just say it's a gas. Let's say it's a container and it's full of air. Well, it feels like the air is continuous in here, or like the gold. If this was a cube of gold, the gold is continuous, but we know now, and Boltzmann knew, that it's really made out of atoms and molecules. That wasn't obvious 120 years ago because you can't see the atoms and molecules. If this was a container of steam, let's say, and you stuck your hand in here. So I took my hand, I put my hand in this container of steam. I'd notice it. I know something was going on. My hand would start to feel hot. There's energy being transferred here, but it wasn't obvious what exactly is the mechanism. Is this a new kind of energy? Is this one of our old kind of energies just in disguise? Boltzmann's big claim and groundbreaking idea was that this gas, if it's steam, let's say, is really made out of atoms and molecules. These gas molecules are running around in here. There's just little particles in here. And what you're actually feeling are these particles striking your hands. Your hands are getting bombarded by these particles, but they're so small and there's so many of them, you can't really tell that there's particles. It just looks completely continuous. So for Boltzmann, this heat energy isn't really a new kind of energy at all. All this heat energy that you're feeling is just connected.
I mean, they knew there's gas. They knew water vapor is gas, right?
Energy. And if it's steam, it's just the kinetic energy of the H2O molecules flying around in here at some rapid speed. And the faster they go, the greater the impact with your hand, which is going to transfer more energy. So the faster they go, the hotter it feels in here. So for Boltzmann, to say that something has a high temperature, if you said
that it's related to the temperature, that the energy is related to the temperature, but that it's the motion of the particle. Why did he think it's the motion of the particle?
that the temperature is large, if it's hot outside, that's kind of redundant. We already had a word for that. We could just say if it's a high temperature, what we really mean is that the average kinetic energy of the gas molecules outside is large. So if a gas is a high
Why not temperature to the 10th power? Why temperature?
temperature, the average kinetic energy of those molecules is large. That's why it hurts when they impact on your skin, because they're transferring kinetic energy to the molecules in your hand. And when your hand absorbs too much energy, these molecules move
Why not temperature squared?
around. Your skin starts to get damaged. You can get burned.
Why not the square root of the temperature?
So this is often referred to as the kinetic molecular explanation of temperature. And the details of this theory were one of Ludwig Boltzmann's biggest contributions to science. But what does any of this have to do with Boltzmann's constant? Well, let's get rid of all of this. You've probably heard of the ideal gas law, PV equals nRT. So remember, T is the temperature measured in Kelvin. P is the pressure, and I'm going to measure this pressure, and I'm going to choose to measure it in pascals. V is the volume. I'm going to choose to measure it in meters cubed. And N, little n, remember little n is the number of moles of the gas. And if you forgot what moles are, and the number of moles is defined to be capital N, the number of molecules in the gas, the total number of molecules in the gas divided by a constant. And that constant is called Avogadro's number. And if you forgot Avogadro's number is 6.02 times 10 to the 23rd, and there's that many molecules per mole. So in every mole of a gas, what we mean by 1 mole of a gas is 6.02 times 10 to the
mole is just 6 to the 10th, whatever. It's this many molecules, this many particles. Mole is just number of particles. It's 10 to the 23rd about particles. When you say mole, you just mean, I guess you mean molecules, but I think you can mean any particle.
23rd molecules. If you choose these units, this R, this gas constant, R is called the gas constant, and it has a value, R has a value of 8.31 joules per mole Kelvin. That's the gas constant R with these units. But these are pretty macroscopic quantities, pressure and volume.
Wait, N is the number of moles in the discussion. What is R?
These units, this R, this gas constant, R is called the
Is it Reynolds number?
gas constant, and it has a value, R has a value of 8.31 joules per mole Kelvin. That's the gas constant R with these units. But these are pretty macroscopic quantities, pressure and volume and temperature and moles. Even moles, talking about 1 or 2 moles, is talking about a huge number of molecules. You're kind of glossing over some of the microscopic details. So an alternate way to write the ideal gas law is P times V equals capital N. So forget moles. Let's say we want to talk about how many molecules there are. Instead of writing little n, let's write big N, number of molecules. We need a different constant because we multiply by the same T. So again, this T is still temperature in Kelvin. P is still the pressure in pascals. V is the volume, again, in meters cubed. N, instead of being the number of moles, is now the number of molecules. And that means we need a new constant here. We need a different constant. That constant's got to be really, really small. The rest of this stuff's the same. P times V and T are all the same. And all I did is I swapped out little n, number of moles, for big N, number of molecules. So this is going to be a huge number we're plugging in this spot now. Instead of plugging in, like, say, 2, if I were to plug in 2 moles right here, the number 2, down here I'd plug in 2 times this. So I plug in 12.04 times 10 to the 23rd. Since this is a huge number, I need a constant that's really small because it's got to balance out. We know that n times r has got to be the same as capital N times this constant because the rest of this is the same. This left-hand side is the same and the t is the same. So if this is all consistent, then n times r has got to be equal to n times this new constant. And that new constant is Boltzmann's constant. It's a lowercase k with a b on it to denote Boltzmann.
Oh, that's interesting. So now you can begin to see, but where is the energy?
Constant. So what's the value of Boltzmann's constant?
So PV over N is energy?
We can find it pretty easily. We know that little n times r has got to equal big N times Boltzmann's constant. So if we just solve this for Boltzmann's constant, we're going to get
little n, number of moles times r, is the number of molecules.
N over big N times r.
So KB is n r over capital N.
But what's little n over big N? Just look up here. We can figure it out. Little n over big N. If I solve this for little n over big N, what I'm going to get is, if I divide.
So little n over big N is 1 over Reynolds number. Reynolds? No, 1 over Avogadro's number.
Both sides by big N, I get 1 over Avogadro's number. Little n over big N right here is Avogadro's number, or 1 over Avogadro's number. So I get that.
1 over Avogadro's times R. So R over Avogadro's.
1 over Avogadro's number times the gas constant, this 8.31, is Boltzmann's constant. And if you multiply that out, the gas constant, which is 8.31 joules per mole Kelvin, and divide by Avogadro's number, which is 6.02, times 10 to the 23rd molecules per mole, you'll get Boltzmann's constant, which equals 1.38 times 10 to the negative 23rd joules per Kelvin. This is Boltzmann's constant. This number right here is Boltzmann's constant. Why do we care about Boltzmann's constant? Well, it allows us to write a more microscopically oriented version of the ideal gas law that focuses on number of molecules instead of number of moles. And this number pops up all over statistical and thermal mechanics. It's one of them.
But the claim is that PV over N needs to be the energy. How? That's the average energy. So pressure times volume over the number of molecules is the average energy per molecule. Well, we can see when we're dividing by N, we see that, but why is pressure times volume the energy? That's all I need to know. Pressure times volume. Really? Pressure times volume is energy?
The most important constants in all of thermal physics, in fact.
So all we need to know now, Boltzmann constant, all we need to know is PV is energy? Let's ask ChatGPT. E equals PV. So it seems like it. So the equation equals PV is a simplified expression used in thermodynamics to describe the energy of a system in terms of its pressure and volume. Specifically, this form appears in console. Maybe somebody made a video of this. What is this?
Big Boltzmann, who was a genius. He lived in the late.
We just watched it. That doesn't help us. So now we need E equals PV. Enthalpy? What is going on here? Okay, let's say it explicitly. Energy equals pressure times volume equals PV. Is this P or rho? Rho V is a constant. Pressure and volume. How to use PV equals a constant. Internal energy heat. Okay, internal energy heat and work. Work equals P delta V. Well, it's the same units. So it's P delta V. Interesting. So let's watch this. PV diagram. Bozeman. It's not Boltzmann. He teaches stuff. Pressure, volume, work. Oh, pressure, volume, work. That's interesting. I mean, pressure, I guess, times volume is work. Did I open this? PV work example. Is this the definition of enthalpy? First law of thermodynamics. Work is PdV. Interesting. PV work. Interesting. PV work. Okay, everybody seems to agree that pressure times volume is work. Everyone agrees.
In this video, we're going to focus on chemistry problems relating to internal energy, heat, and work. So let's start with this one. Calculate the change in the internal energy of a system.
Yeah, I don't care about an example. I want to see derivation.
Volume work in closed systems. So let's say we have a closed system. So that's a system which can exchange energy with the surroundings, but
I don't like the way he's explaining.
Be deriving the formula for pressure volume, otherwise known as PV, work. And
that's good. Deriving is good.
This is a common thing that you will.
Right. So force times displacement is work. So he's going to turn force times displacement into pressure times volume. Let's see.
We'll discuss in introductory.
I mean, you can already begin to see this is X, but it's going to end up being volume.
Thermodynamics courses. And the very first place that we're going to start is turning to the definition of work that we learned from high school physics, in that work is equivalent to a force times a displacement. And as we get more nuanced, we will recognize that force is really a vector and our displacement is also a vector. So when we take the dot product of these two vectors, we end up with a scalar quantity, which is the amount of work done by our system. And
that's very good.
The first thing that we're going to be turning to, again, looking back to physics, is the definition of pressure. Pressure is defined to be the amount of force that a fluid is exerting over some given area. And in addition to that,
that's good. So the definition of pressure is force per area. That's good.
The volume, if we were to consider a piston with a constant area and a coordinate going down into the piston of x, we can define the volume of our cylinder to be equivalent to area to the base a times the height x. And so with these two things,
that's good. So the volume is the area times the displacement. That's good. So we can redefine A is V over X. So replace A with V over X. So V is here and X is here, and F times X over V. But let's see.
out of the way, when we begin to look at differential control volumes, we were to look at the amount of work done. We take the derivative of work, we end up with force times dx. And as we turn to these definitions, if we rearrange this and multiply both sides of the equation by a, we will recognize that F is real equivalent to pressure times area, and X.
So how did he get this? I mean, oh, he rearranged it. So F is just PA, P times A. And A is V over X. Let's see what he does. Anyway, F is P times A. So you have P times A here.
Here is equivalent to volume divided by area. And D.
So from this equation, he gets X is V over A. That's good. So that's X. So he's going to replace dx with, since A is a constant, so it's going to be dV over A, and F over A is P, so it's PdA, it's PdV.
dx is equivalent to dV times 1 over area. If we
Yeah, so dx is dV over A.
Assume area is constant.
Assume area is constant, that's true. So he's going to replace dx with this dx, or the opposite. He's going to replace this dx with this dx. So it's 1 over a dv. So it's so f over a dv, but f over a is p, so it's p dv. Very good.
And so if we were to plug in now,
but you don't need to go to the differential form. You can just go to the original form. W is E. So it's E equals Fx. X, from here, X is V over A. So it's V over A. So it's just V, and F over A is P. So it's just PV. So E equals PV, and we're done.
Our definitions of dx and force, what we will
He's going to end up integrating and getting the original result.
see is that the work done in our differential control volume will be equivalent to pressure times area, which was F, times dx, which was 1 over area, times
pressure times area. What do you mean pressure times area? Oh, he's just dividing. This is A over A. Okay.
dV.
But where do you get what's going on here? He's replacing F equals PA. From this, he has F equals PA. Wow, he's really confusing it. F equals PA. So this is PA, and dx is 1 over AdV. So the A goes away. You're going to end up with PdV.
And so what we'll recognize here when we have a constant area is that the area terms cancel out, and we're left with the change in work inside of our little control volume is equivalent to P times dV. Now, what we're going to do is integrate both sides of our equation to solve for the total amount of work done.
Are you out of your mind? So why did you differentiate?
During an expansion or contraction. And what we're going to find is that we have V1 to V2, and work is ultimately equivalent to negative integral from V1 to V2 of pressure times the change in volume of your process. And in the case when pressure is constant, we can pull out pressure from this integral, but generally we will leave it in this final format. And so to plot this out, because typically you're going to be asked these types of questions on exam.
Because the pressure is not a constant. Mm-hmm.
Exams, if we have graphs of pressure and volume, what we're really calculating as we are taking this integral is the area under the curve of P2, P1, V1, V2. And the reason we have this negative sign right here is because depending on which direction we are headed, if V1 is smaller than V2.
Very interesting. So he says, this is very interesting. So he says that this is V1, V2. At V1, you had P2. It should be at V1, you should have P1. But I guess it's the higher pressure. So what actually took place here? So let's say all other things remain the same. So we went from a certain pressure at a certain volume, and we increased the volume, so we decreased the pressure. So nothing really changed. We just changed the shape. We increased the volume, so we decreased the pressure. Yeah, there's work done here. This is not free. You cannot increase. Either this was under pressure and you let it go and it grew, so you received work, or you injected work or energy. Okay.
If we are compressing our system, then
this is, yeah, you're compressing. No, you're not. You're increasing the volume. No, there's no directionality. If you're compressing, it's this way. If you're compressing, right, this is the arrow. If you're compressing, then you're increasing the pressure.
this area will be negative because we're moving to.
This is basically, you could say this is PV equals nRT. If all other things remain the same, then P times V is a constant. If P times V is a constant, then this is natural log.
The left, work is done on the system. And then if V2 is greater than V1, work is done by the system. Example, this would be the combustion engine inside of your car. It is doing work on the system. It's being done by the system to deliver the power that your wheels put onto the road to drive you to San Francisco. So this is a common graph you will see people draw. The reason we want to leave it in this format is because quite often the pressure is not constant, so we need to keep it inside of our integral. We are essentially, and if you can remember, this is a very important point, we're just taking the integral end of the curve. The direction matters extraordinarily because we're defining whether or not work is being done on or by the system. And so in the case when we're doing compression, we are putting work into our system, we're increasing its internal energy. When our system is expanding, we're doing work by our system, in which case V2 is greater than V1. And so the work would be leaving our system, so it would have a negative quantity. And so that's going to wrap things up for this introduction to work, or pressure volume work in thermodynamics. I hope this helps, and thanks for watching.
And thank you for watching. Okay, this isn't whatever.
Diagram. That's my pressure axis. This is my volume axis. Just like that, I have pressure and volume. I showed several videos ago that if we start at some state here in the PV diagram, right there, and then I change the pressure and the volume to get to another state, and I do it in a quasi.
So I'm wondering, what year was this? It doesn't say the year. If you hover over September 25th, as if September 25th is so important. This is from 2009. Right now it's 24. So this is 15 years ago. I think Bill Gates gave them money. Gave Khan money. Gave him, I remember he gave him like $1 million in those days. Okay, but I don't. Oh, this is enthalpy, thermodynamics, chemistry.
Static way. So essentially, I'm always close to equilibrium. So my state variables are always defined. I could have some path that takes me to some other state right there.
Keep Khan Academy free. $26,000 raised. Why do you need money? Why don't you just get money from YouTube? You have 8.56 million subscribers. Why do you need people to give you money?
And this is my path. I'm going from this state to that state. And we said, well, we show that if I just did this, the work done by the system is the area under this curve. And then if I were to move back to the previous state, and then if I were, by some path, just some random path that I happen to be drawing, the work done to the system would be the area under this light blue.
So this is work and this is work, but this is right as we increase. Well, you look at this is increased volume and decreased pressure, but you don't know if you did work or the system did work. You don't know if it's positive, if it's net positive or net negative. But it's a certain amount of work, the area under the curve, and on the way back, it's less. So whatever happened this way minus this is the energy loss. So enthalpy is the energy loss.
Blue curve. So the net work done by the system ended up being the area inside of this path.
Yes, I agree.
So this is, let me do it in a different color. The net work done would be
Red.
the area inside of this path. When I go in this clockwise type of direction. So this is the work, the net work, right? Net work done by system, done by system.
We don't know
Done
if it's negative or
by
positive.
the system. And now we also know, so that's, well, we also know that if we're at some point on this PV diagram that our state is the same as it was before. So if we go all the way here and then go all the way back, all of our state variables will not have changed. Our pressure is the same as it was before. Our volume was the same as it was before. We went all the way back to that same point on the PV diagram. And our internal energy is also the same point as it was before. So our change in internal energy over this path, you're gonna have a different internal energy here than you had here. When you go around the circle and you get back, your change in internal energy is equal to 0. And we know that our change in internal energy, it's defined as, and this is from the first law of thermodynamics, the heat added to the system. So it's the heat added to the system minus the work done by the system. Now, if we go in a closed loop on our PV diagram, then what's our change in internal energy? It's 0. So we get 0 change in internal energy because we're at the same state is equal to the heat applied to the system minus the work done. Or, and I've done this little exercise multiple times. I think it's probably the 4th or 5th time I'm doing it. We get that the heat added to the system, if we just add W to both sides, is equal to the work done by the system. So this area under this, in between inside of this path, I already said it's the work done by the system. And if you don't remember even where that came from, it was, remember, pressure times volume times change in volume is a little incremental change in work, and that's why it relates to the area. But we've done that multiple times. I won't go there just yet. But so if you have any area here, some heat was added to the system, some net heat. Right? Some heat was added here and some heat was probably taken out here, but you have some net heat that's added to the system. And I use that argument to say why heat isn't a good state variable, because, and I had a whole video on this, that if I define some state variable, let's just say heat content. Let's say I want to define some state variable heat content. And I would say that the change in heat content would of course be equal to the change in heat. And that's what I'm defining. If I'm adding heat to the system, my heat content should go up. But the problem with that heat content state variable was that, let's say over here, I say that the heat content, let's say that the heat content is equal to 5. Now, I just showed you that if we go on some path here and we come back and there's some area in this little path that I took that some heat was added. So let's say that this area, let's say that this area right here, so this is Q is equal to the work done by the system. Let's say it's equal to 2. So every time, if I started heat content is equal to 5, that's just an arbitrary number, and I were to do this entire path, when I go back, the heat content would have to be 7. And then when I go back and do it again, my heat content would have to be 9. And it would have to increment by 2 every time I do this exact path. It would have to increment by the amount of area that this path goes around. So heat content can't be a state variable because it's dependent on how you got there. It's a state variable, and remember this, in order to be a state variable, if you're at this point, you have to have the same value.
I don't know what he's talking about.
Short for pressure volume work. And this is a topic we introduced in the last lesson on the first law of thermodynamics. The most common type of work we would cover is this pressure volume work. But we paid it lip service and we didn't go too heavy into it. And that's because many of you don't need to go any further into it than that. But if it was a point of emphasis in your class, especially oftentimes if you're a chemistry major, then it is usually something that's expounded upon a little bit more than I did in the last lesson. And that's what we're going to cover here. And specifically calculations involving work. If you want to add Q and W, oftentimes you're going to be doing this in joules. And the problem is that work is not going to come out in joules if you use the standard units of pressure and volume that you're often given, pressure in atmospheres and volume in liters. An atmosphere liter is not the same thing as a joule, and you're going to be trying to add apples and oranges if you're trying to add Q and W in that case. So
yeah.
PV work stands for is pressure volume work, right? So that P and V is pressure volume work. Right? And this is a very common type of work that's related to an expansion or compression of a gas, right? So we've been talking about the first law of thermodynamics. We talked about it as the transfer of energy via heat and work. This is the first real deep dive we're going into any type of work, pressure volume work. And we spent a lot of time in the last unit talking about properties of gases, right? So now we want to be able to identify not only the pressure or volume or temperature of a gas or the amount of a gas, but how much energy is transferred in when a gas.
He needs a plosive protector, whatever. Like he blows into the mic and you can hear his P's really loudly.
Gas changes volume. right? So this figure that I've drawn here is an example of a gas compression. So you have some cylinder that has some gas sample. So the green here is the gas, and it's contained in this cylinder that has a movable piston, right? So this piston, this little platform, is movable.
You can hear the peas exploding.
And the gas sample is contained underneath the movable piston. Now it's at an initial height, which I'm calling h sub I, and that gives the gas an initial volume of v sub I. Now let's say that you come in and you apply an external pressure to that piston such that you compress the gas sample, right? So you compress the gas sample such that its height decreases the height between the bottom of the container and the piston, and you end up with a final volume Vf that's less than the initial volume Vi, right? Now we know from our simple gas laws that if you compress the volume of a gas, that pressure is going to increase, right? So as you decrease the volume that's available to this gas, you start to increase the pressure, right? They're inversely proportional. So that change in this, the initial volume and the final volume of the gas is going to be our change in volume, right? So we'll have a delta V. This little slice here is representative of our change in volume. So now how do we identify how much energy is applied to the system by constricting its volume in this way? So let's look at that. So we've defined work. Work is going to be a force acting over a particular distance. So as an equation, that's going to be the force applied times the distance, right? So we'll have force times distance as our definition of work, right? So now how do we apply this definition to our specific scenario here, right? Well, I'm going to use the variable W for work, right? There's going to be an applied force here, right, for the gas sample. And the distance that we're talking about is the distance that this piston travels, right? So really what we're looking at here is the difference in this height, right? So the difference between HI and HF, that's going to be our difference in height. I'll call that delta H. So we're really going to have force times delta H, right? So if we can quantify this product between the force and the change in height, then we can define the work that's been done by the system using the definition of work. So what we're going to have to do, though, is to...
It has to end up being an integral. I don't understand why they say PV is energy. P delta V is energy, but PV... I mean, it just doesn't make any sense.
To relate this to properties of our gas.
I mean, everybody says PV's work.
Sample, right? Properties that we can calculate, like pressure. So what I want to do is relate this definition of force to pressure, right? So if we consider the definition of pressure, right, we know that pressure is equal to force per unit area, right? We looked at that in the last unit when we talked about pressure. So we know that it's force per unit area, right? We can actually do some algebra here to isolate the force, right? So force is going to be equal to pressure times the area, right? And by area, in this context, we're talking about the surface area of the cylinder, right? So that pressure is acting along the surface area of the cylinder. So what we can do here is use this definition of the force, right? Plug this guy back into the work expression, right? So if we do that, then we end up with work is equal to pressure times area times delta H, right? All I've done here is just substitute this definition of the force. Now it's just pressure, right? Pressure times area. Plug that into our original equation for the work to get this new equation for the work. That includes the pressure, right? So pressure times area times height, right? So if we think about what this product here is, right? So area times delta H, right? This is just going to be the volume here, right? So if we take delta H, right? So this height here is delta H. You take the surface area of this cylinder, right? Times the height. That's just the volume of a cylinder, right? So this product is just the volume.
No, it's the dV. It's not the volume. It's the delta volume
of the cylinder.
I mean, how can you talk this way? How can you be so inaccurate? This is so confusing. Anyone listening to you thinks... One second, let me check the battery. Anyone listening to you thinks that PV is work. It should be P delta V because P is not a constant if V is changing. I mean, so many things are changing simultaneously. You could say it's PdV or P delta V.
Right, so the work is going to be equal to the pressure times the change in volume. Right, so this is great. So now we have the work defined in terms of two state variables for gases that we're very familiar with, the pressure and the volume. So now the only thing that we need to do is to make sure.
So here you said volume of cylinder, but then you wrote the change in the volume of the cylinder.
That this definition of the work gels with our sign conventions for the work, right? So we talked about in the last video that for work, if work is done on the system, then that's going to be a positive work, right? Versus if work is done by the system, that's going to be negative. So
okay, that's just the definition.
We need to make sure that this gels with that sign convention. So in order to
gels?
Compress a gas, you have to do work on the system. You have to apply external pressure in order to compress a gas to a smaller volume, right? So with that being said, if it's going to be VF, if delta V, right? So let's kind of expand delta V here. Delta V is just going to be VF minus VI. In the case of a gas compression, VF is less than VI. So that means you're going to end up with a negative delta V. So in order for us to correct for this this sign that we're going to get from delta V, we're going to put a negative in front of this expression, right? So work is going to be equal to negative P delta V, right? And this is going to be your expression for the work, for pressure volume work, right? So this is our expression for PV work. Right? Like I said, it's very important for us to include that negative sign because in a compression, we want the work to be positive. So, since we're going to get a negative from delta V, that's going to cancel out with this negative out front. That'll give us positive work. And for an expansion, right, where the...
But what's the definition of delta V? What's the direction of delta V? You're not saying if you're decreasing or increasing. So I'm assuming your delta V is positive, so you're increasing the volume. If the pressure is positive and you're increasing, that doesn't make any sense.
the gas would have to do work in order to expand. That's going to be a negative value that would gel with our sign convention that we've established for the work. Okay, so now that we have this.
Right, that's why it's negative, because this means you're decreasing the volume. So if the pressure is positive and you're decreasing, then the work is positive. So if delta V is decreasing, meaning V2 minus V1 is negative, then it becomes positive. Something like that.
This expression, let's look at some examples. So first example problem, this says calculate the work done when a piston expands against a 1 atm of pressure from 11.2 liters to 29.1 liter. Right. So we have a gas expansion. Right. So we know we need to use our expression that we just got on the previous slide. Right. We got
I don't care.
Can be broken down into two different forms. When we change the energy, that change has to come either from heat or from work. And the sum of heat and work give us the total change in the energy of a system. The goal for right now is to spend a little more time focusing on the details of work. So remember, what we've seen is that work, a differential change in work, comes from changing the energy levels of a system without
What is this slash through the D?
changing the occupation of those energy levels, without changing the probability that those states are occupied. So this is the idea of work that we're going to focus a little more attention on. So if we do some work, it's always done by changing the energy levels. We can think about how we might change the energy levels for a molecule. So imagine you've got a molecule or a whole bunch of molecules that form some material. There's a lot of different ways you can think about changing their energies, doing work on them. I can take those molecules, I can twist them or stretch them or modify their shape in some way. So I'm doing mechanical work on them. I might take those molecules and lift them up in the gravitational well, so I change their gravitational energy. I can change their electrical energy if I put them next to a charged particle, or I put them in an electric field. If the molecules themselves have charges, I've done electrical work. I've changed their energy in that way. Or the case we're going to be more interested in for right now is pressure volume work. If what I have is a gas, even if it's not a gas, but if I have some...
I don't know what he's talking about. It looks interesting, but I need...
Help that I've recently realized is actually extreme. There's a lie that goes around in self-help that I've recently realized is actually extremely dangerous. Now, self-help often espouses the idea that having a growth mindset and persevering no matter what happens is going to get you to success. And I myself have spoken about the importance of having a growth mindset ad nauseum on this channel. But while it's extremely important, it's also really important to clarify that that is only one of multiple elements to success. And recently I've watched somebody who's kind of like a friend of a friend self-immolate, basically set their life on fire because of the lie that all you need in order to succeed is to just keep trying. So in this video, I'd like to share what I personally think is the formula for success and how to avoid ruining your life by only focusing on one of the multiple elements of that formula, all the while hopefully providing some concrete examples.
Wow, a lot of disclaimers.
Now, when we think about what it takes to succeed, obviously human behavior
Wait, she didn't introduce herself.
and success outcomes are impossible to predict. But I think that there is a formula that can get pretty close. And that is having an interest that's compatible with your natural capabilities, persevering, having that growth mindset, and experimentation, working with different things through trial and error. If you have those three elements, if you have an interest that you're naturally quite good at, and you put in a lot of work into it, and you experiment with ways to optimize how you're doing at that thing, there's a pretty good chance you're going to be successful at it. Now, of course, we're just talking about internal factors here. I'm not talking about external factors like socioeconomic resources or luck or having wrong place, wrong time. Those things definitely do factor in and inhibit or help a person's ability to succeed. But right now, I'm really just talking about internal factors. So breaking down each component, starting with having a compatible interest, an interest that's compatible with your natural capabilities. I don't believe in fixed trait mindsets. I don't think there's much of a benefit in telling yourself, this is what I'm good at and this is what I'm bad at. I don't think inborn talent matters as much as the amount of effort that you put into something. And there is a body of literature that supports that notion. But there are certain interests that come easier to us than others, that may be more compatible with our natural capabilities. Some come with a lot more ease than others. Others come with a lot more effort on our part. For example, can a person who is short in stature get really good at basketball? Yes, I'm sure they can. I'm sure if they put in a lot of work, they can surpass even their tall peers. But it might be a lot more work than somebody who's naturally tall. Or to give you another example, when I was in middle school, I really wanted to get into singing, and I was not naturally good at singing. When I told this to my parents, they were like, Anna, you're not good at singing. Don't do this. So to prove them wrong, I joined choir. And guess what? By the end of the year, my parents came back to me and they said, you know what? Actually, we were wrong. Yeah, you're right. You put in the work, and now you're actually pretty decent at it. But contrast that with writing, for instance, which has always come naturally to me, which I've been told my whole life that I'm good at. It would be so much harder if instead of trying to be a writer now, I were trying to be a singer. Could I maybe get good at it? Could I maybe succeed? It's possible. But why would I try to do something that comes so much harder to me when focusing on something that comes easily is not only more enjoyable, but it allows me to succeed at that thing much more rapidly. So that is one element of the formula for success that I think is really important, is you need to choose what you want to succeed at very carefully in a way that maximizes your ease, in a way that's the path of least resistance, that isn't going to be so hard for you. The second component is indeed persevering, continuing, keeping up this growth mindset of, I'm going to...
All right.
Or welcome back. If you don't know me, my name is Anna. I'm a clinical psychology doctoral candidate, and I make videos about real-life applications to psychology, usually. But today I'm going to do a little bit more of a fun video because I just wanted something easy, something I didn't have to write up and research, honestly, because classes started back up. So today we're just going to look through my 23andMe data because I get questions pretty much every day about my ethnicity. A lot of people think I'm Asian. I've been compared to Momo, who's I believe a K-pop artist. I've been compared to Anna for the Vampire Diaries, this other woman who I don't remember from The Girl in the Train, or I don't remember the name of the movie. So the point is, people think I look like a lot of different people, I guess because of my dark hair and pale skin. And today I get to actually show you what my ethnicity is, which, you know, if you don't know yet, I am Romanian. That is my nationality. That is what I identify as. We're really looking through my entire genetic makeup. But first, I want to tell you about today's sponsor, which is the 6421 journal right here. I've been using it for the past few weeks, and it really is an amazing mental health journal. If you don't have the time or today you feel great for most productive, meaningful exercising. And once exercising is a priority, it can make
transform these shoulds into musts. Example of something I put under. So for example, this day I wished for a fun, chill get together. And it can be really like a summary of things that you achieved. It could be things that you're happy with, the main goals of the month, and then using daily things you specifically want to focus on. And this 17 freedom pages on the other side. So you can really use these. I really do highly recommend this. I've been using it ever since I got it in the and I am a little tiny bit Greek.
Half of her video is advertisement. Jesus. So let's see. I thought she's Jewish. What's her name?
View your ancestry composition. So I'm 69% Greek and Balkan, 29%
Chinese. Eastern European. Oh, that's Jewish. So she's a third Jewish.
Eastern European and 0.6% Chinese. So Greek and Balkan basically means, if you don't know where the Balkan region is, it's in the southeastern area of Europe. And I am a little tiny bit Greek. I know that about myself, but Romania also qualifies under the Balkan region. So I think that's probably the bulk of it. And it's interesting.
Oh, she's Romanian.
Because Romania is also in Eastern Europe. It's also Balkan and it's also Eastern European. So really, Greek and Balkan and Eastern European are kind of redundant, but whatever, they had to split it up some way. So looking at the report for Greek and Balkan. Okay, so yeah, this is the map of where from Romania I am, and highly likely match that I'm from Romania. Yes, I would say so. So I was actually born in Bucharest, but it says that my strongest genetics are from Moldova, which is actually where my dad is from. He's from Suceava. So, this makes a lot of sense. I know that also my grandpa and my grandma on my mom's side were born in this little region here. Moldova, as Moldova the country, so there's Moldova within Romania, and there's Moldova, which is its own separate country, which
So I don't think she's Jewish.
kind of like a combination of Romanians and Russians. So it says I also have some genetics from there. And where's the Greek? Because I know for sure that I also have some Greek in me. That's weird. It took away the likely match with Greece, but I know for a fact that I have a great-great-grandmother from Greece. So that's interesting. From my knowledge, I am 6.25% Greek, but who knows? Okay, so I'm gonna go back and look at the part that says Eastern European now. So right now I already have kind of an idea that probably the southern regions of this map are gonna be from my mom and the northern regions from my dad. So 29% Ukraine. So Ukraine seems to be the most possible match for this one. 29% Ukrainian. That's actually quite surprising. I was not expecting it to be that high, but I guess my dad is right on the border. And then the 0.6% Chinese. Yeah, wasn't sure why I was showing just Chinese because on the laptop version it shows 1.5% East Asian. So it says 0.6% Chinese, 0.4% Japanese, 0.3% Korean, 0.2% Manchurian and Mongolian, and then also 0.4% Ashkenazi Jewish. So as you guys can see, I am not
Oh, she is 0.4% Ashkenazi Jewish. That's it.
Asian, not in any sense of the word, but I guess like genetically a little bit. And it's really funny because sometimes people say that I look Asian when usually they're white people. Usually they're white. And I know it's been shown by science that we are better at seeing within group differences. So like white people are better at seeing differences between white people. Part of that is exposure because you're not exposed to those people as much. But I've noticed that sometimes when Romanians don't instantly recognize me as Romanian, which they usually do, like I have had people come up to me and say, "Oh, are you Romanian?" just like out of thin air before. But sometimes when they think that I don't look Romanian enough or they think that I look Asian, it's like with this little tinge of racism, like, "Are you sure you're Romanian? You don't really look like us," that kind of thing. And it's actually really funny because when I was in Italy a couple years ago, we walked into my boyfriend's host family because he had spent a year in Italy. And as soon as I walked in, they said, "Tu sei japonese," which basically means you're Japanese, before I even said anything. So it's a little jarring how some people think that I look Asian, but I mean, I guess I get it. I personally don't know why I do, because as you saw based on my genetics, it's not very substantial. But I'm very proud of my Romanian heritage, very proud of all of those.
Anyway, she is interesting. She has interesting videos.
Grant, Amy, Rugg.
That's not what I want. I wanted to go back to today's video. Wait, what's going on? I think we are here. Okay. So we took a detour. I got lost in the detour. So energy equals KT because PV equals nRT. It comes from PV equals nRT, so PV is energy. So energy equals nRT. NR is just K, so it's just KT. So it's actually very simple. So this equation it comes out of PV equals nRT. This is PV. No, it's not. This is PV over N. PV over the number of molecules. N on the side, nRT, N is the number of moles. So if you... Right, we saw the derivation. It's very straightforward. This is really very simple algebra. So, assuming this equation, which he did in the comments, he did explain the derivation very quickly, in quick succession. I mean, we saw his simulations. The question is, so he says here that it's derivable. This is the Boltzmann-Maxwell distribution. So this is the last piece of the puzzle that I'm not sure about that I need to still investigate. So this ends up being really very simple. E equals KT is really very simple. The average energy of any molecule in a gas is just KT. If you believe that PV equals nRT. So, which I think makes sense, and I think it's empirically verified or something. Who knows? Let me take a sip of some poison. Oh my god. Anyway, so okay, so we have this. And this is derivable. We can derive this. This is very straightforward. This is straightforward. Assuming this equation, then we have this, and now he's converting this to this, because E, average energy, is just 1 over, E equals KT, so that's KT. And this epsilon becomes dE, and E over E again becomes E over KT. It's fine. Everything is correct so far. So the probability of any molecule having this energy, right? The probability so he doesn't want it to be, right? This is an infinitesimal number, obviously, because of dE. It's just a little sliver of energy, but it's really but you this doesn't mean anything. You need to say you need to integrate. This is incorrect. You need to integrate from E1 to delta E. That's still infinitesimal. You can't. This is infinitesimal. You cannot. This doesn't mean anything. You need to actually say E1 to E2. You can't say this. This doesn't mean anything. The probability. This is an infinitesimal probability. This is dP. This is not an actual number. This is 0, because dE tends to 0. So this is 0, and this is 0. You don't want. This is meaningless. I don't think a mathematician. I mean, both sides are 0, but fine. Okay.
The solution to which required a radical rethinking of the physics of the very small.
Wait, what?
It clarified the somewhat mysterious thermodynamic concept. Statistical mechanics provided powerful explanations for phenomena arising from the interaction of many particles. It accounted.
So this was good for thermodynamics up to molecules, up to atoms, I guess, up to a gas.
For the relation between pressure, volume, and temperature of an ideal gas. It clarified the somewhat mysterious thermodynamic concepts of entropy. But when these ideas were applied to situations involving electromagnetics, a serious problem arose, the solution to which required a radical rethinking of the physics of the very small.
No, it's not good to give an introduction, because now you put everyone to sleep. You should use the Socratic method. You should have the student face the problems themselves. Don't introduce us. Don't give introductions. Just show us the problem. Ask us to solve the problem. Don't introduce. Don't tell us where it's going. Don't tell us this is going to be hard, easy, whatever. I don't care. Just tell us the problem. Introduce the problem. Because until now, you've been discussing distribution of energy in an ideal gas or something, which was very interesting. This is the probability that any molecule will have any energy. I can integrate this from E1 to E2 to get any distribution of energy. Okay, what is that good for? I don't know.
The solution to which required a radical rethinking of the physics of the very small. According to electromagnetic theory, when an electric charge is accelerated or jiggled around, it radiates an electromagnetic wave. When this wave encounters other charges, it exerts forces that cause them to jiggle in response.
This is not according to theory. This is what Hertz discovered, isn't it? Didn't Hertz discover this? I don't think anyone predicted it. Did anyone predict this? I don't know. Is this from wave theory? I guess you could say this is just wave theory from wave mechanics. So if assuming wave mechanics, maybe you can predict this behavior.
They would also radiate their own waves, but we don't show that in this animation. Given that electromagnetic radiation from our sun is the primary energy source for our ecosystem, it's clear that these waves carry energy. Therefore, they should somehow fit into our chunks of energy analysis as additional places to transfer energy in and out of. Consider a piece of metal which consists of an array of more or less fixed atomic nuclei and bound electrons, represented by green dots, and a collection of conduction electrons, which are more or less free to move around, represented by red dots. These particles will have average kinetic energies proportional to the temperature T of the metal.
Okay.
The low-mass electrons will travel with especially large velocities and accelerations. They're charged, so they'll produce radiation. Therefore, we see that there will be a close relation between the temperature of a material and the radiation it produces.
No. What you're saying is that forever this will glow. And that's not possible. This means that this has infinite energy inside it. So that's not possible. So this has to, if it radiates energy, it needs to cool down. So the idea that an atom keeps radiating energy like for no reason whatsoever, just because it exists, makes no sense. So that's impossible. So scrap that. That's incorrect. So your notion that an accelerating charge is radiating must be incorrect. There's a flaw in that assumption. It might be correct when you run experiments, but it's not correct in your atomic model. Something about your atomic model is incorrect, because otherwise it should have given off infinite energy. At this point already you have a problem. You don't need to go any deeper. You're already wrong. You already know you're wrong. So you have to rethink. At this point, you have to rethink everything you said. Everything you said is wrong, meaning the whole picture is wrong. And I would suggest it's the atomic model that is wrong, namely that an accelerating electron, namely that the electron is accelerating in the first place. The electron is not accelerating. It's waving, but it's not experiencing acceleration. It cannot be either. It's not, something in everything you said is wrong. Can't be that everything you said is right, because it would violate conservation of energy. Every piece of material would always produce energy, according to you. Unless you say it's going to cool down, it's going to stop. and slow down until until it stops vibrating. Maybe then.
This connection between temperature and radiation is readily apparent when an object is heated until it glows. The initially
What are we looking at here? What the heck is this? I mean, this I know. This is an incandescent light bulb, and this is just a glowing piece of steel. But what the heck is this? I don't know what that is. What is that? It's a tube with something glowing in the center. I don't know what.
reddish glow becomes whiter with increasing temperature. Suppose we have a box enclosing a vacuum.
Where are we going now? There's so many thought experiments. Where are you taking us?
Sides of which are made out of some material at a temperature T. Suppose we have the initially reddish glow becomes whiter with increasing temperature. Suppose we have a box enclosing a vacuum, the sides of which are made out of some material at a temperature T. Suppose we have a box enclosing a vacuum, the sides of
a box enclosing a vacuum?
Increasing temperature. Suppose we have a box enclosing a vacuum, the sides of which are made out of some material at a temperature T.
Okay, the sides are T, inside is a vacuum. The sides are temperature T.
Box enclosing a vacuum, the sides of which are made out of some material at a temperature T. The charges in the material will be in thermal motion, and the box will be filled with radiation. The particles making up the box contain kinetic energy, and the radiation in the box contains electromagnetic energy. We've discussed the relation between temperature and kinetic energy. Now we want to see what the relation is between temperature and electromagnetic energy.
Okay, until now we were just dealing, I thought, with a gas. But I guess it would also hold for a solid, except for Boltzmann equation, KT, that was for a gas. Energy is equal to KT. That's a gas equation. That's not a solid equation. You can't use energy equals KT. Can you? Jesus. This is impossible to learn like this. There's just way too many questions.
Towards this end, we need to consider the wave aspect.
Okay, we need to stop here. We've been here for 3 hours. Oh my God. I want to tell people, anyone who has a question, please watch my video. But I cannot tell them. It's impossible to tell them. YouTube doesn't allow to link to other YouTube videos. Can you believe it? They don't allow you. No, you will not link other YouTube videos. No, absolutely not. Why not? I don't know. You cannot link YouTube videos. No, we don't allow it. Because you're going to link something that we don't approve of. So?
Welcome to Quantum Mechanics.
Did you approve this content? Terrible. I made a video review of this video if you want to watch it. Yeah, they're not gonna let me put it here. Maybe I can make a tiny URL and then they're not gonna block it. Let me see. How do you make a tiny URL? Make a tiny URL. URL shortener, branded short links and analytics. I don't know how to do that. I'll do that later. For now, just make the comment without the link. It's like a 3-hour. I made a 3-hour step-by-step video review of this video. If you want to watch it, then look for, and I'll give you the name because YouTube is so amazing. So I need to modify the name because we ended up just doing this. So let's take just the name, copy, and go and edit today's video. And that's going to be the name. So with the same name, if you want to watch it, it has the same name as this video. Comment. Okay, whatever. All right, we'll stop here. This was painful enough. So we'll see you next time. Bye.